Every detail in this story comes from real scientific research and observation. There is a signal traveling through space right now that will never arrive. It left a machine the size of a school bus, moving at 31 kilometers per second, falling through the upper atmosphere of a planet 1.5 billion kilometers from Earth. The signal carried temperature readings, pressure data, the molecular composition of a sky no human eye has ever entered. And then, at 11 hours, 55 minutes, and 46 seconds Coordinated Universal Time, on September 15th, 2017, it stopped. Not because the machine ran out of things to say, because the machine no longer existed. For 20 years, Cassini-Huygens traveled through the solar system, executed 294 engine burns, completed 127 close flybys of Saturn's moons, and returned 635 gigabytes of scientific data. It discovered active geysers erupting from the south pole of a moon called Enceladus. Water vapor and ice particles launched 200 kilometers into space, carrying organic molecules and molecular hydrogen. It mapped the surface of Titan through cloud cover so thick that no optical instrument had ever seen the ground below. It watched a storm system on Saturn grow until it encircled the entire planet, a band of churning atmosphere 45 degrees wide, sustained for nearly a year. And then it was told to die. Not because it failed, because it succeeded. The decision was made years before the end. Cassini's fuel was running out, and without propellant to control its trajectory, the spacecraft would eventually drift. And if it drifted into Enceladus, with its subsurface ocean, its hydrothermal vents, its organic chemistry, it would contaminate the most promising candidate for extraterrestrial life in the solar system. The same was true for Titan, with its lakes of liquid methane and its atmospheric chemistry that mirrors in strange and distant ways the chemistry of early Earth. So the people who built Cassini chose to destroy it. They called it the grand finale. 22 orbits through a gap no spacecraft had ever entered, the space between Saturn's innermost ring and the top of its atmosphere, a corridor 2,400 kilometers wide, each pass collecting data that could not be gathered from anywhere else. Gravitational field measurements precise enough to map the distribution of mass inside Saturn's interior. Magnetic field readings close enough to begin answering a question that had puzzled planetary scientists for decades. Why is Saturn's magnetic axis so nearly identical to its rotational axis when every known planetary magnetic field is tilted? The answers came in fragments, arriving at Earth after the full transit time light required to cross that distance. While the signal was traveling, Cassini had already moved, already taken another measurement, already fallen a little deeper. On the morning of September 15th, 2017, the last signal arrived at the Canberra Deep Space Network antenna in Australia. Engineers in Pasadena, California, watched a line on a screen go flat. Some of them had worked on the mission for more than 20 years. Some had joined the project as graduate students and were now senior scientists. They had spent their careers learning everything there was to know about a machine that no longer existed. What remains of Cassini is not wreckage. There is no debris field, no crater, no monument. The spacecraft was moving fast enough, and Saturn's atmosphere is thick enough that the aluminum and titanium and gold that made up its structure were broken into atoms and absorbed into the planet itself. Cassini is Saturn now, dispersed into a hydrogen and helium atmosphere 11 times wider than Earth, mixed into clouds of ammonia and water ice, somewhere in a band of atmosphere that no instrument will ever reach again. Tonight, this is the story of how that happened. Not just the final morning, but the 20 years that made it inevitable, the science that required the sacrifice, the people who made the choice, and the 44 minutes during which a machine fell through the atmosphere of a ringed planet 1.5 billion kilometers away and kept sending data until it physically could not anymore. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Saturn is the 6th planet from the Sun, orbiting at a mean distance of 1,432,000,000 kilometers. At that distance, sunlight takes approximately 79 minutes to arrive. The planet itself is a gas giant, a body composed primarily of hydrogen and helium, with no solid surface, its interior transitioning gradually from gas to liquid, to a state of matter that does not exist naturally anywhere on Earth. Metallic hydrogen, a phase in which hydrogen atoms are compressed so tightly that their electrons move freely, generating the magnetic field that surrounds the planet and extends millions of kilometers into space. Saturn is the least dense planet in the solar system. Its mean density is 687 kilograms per cubic meter, lower than liquid water. In a body of water large enough to hold it, Saturn would float. This is not a metaphor. It is a direct consequence of the planet's composition, 96% hydrogen and helium by mass, the same elements that dominated the early solar system before heavier elements condensed into rock and metal. Saturn formed from what was left after the Sun took most of it. Its rings extend outward from the planet's equator to a distance of 482,000 kilometers, but the main ring system, the A, B, and C rings visible through even a small telescope, spans only about 60,000 kilometers of that and is almost impossibly thin for its width. In most regions, the rings are between 10 and 30 meters thick. They are made almost entirely of water ice, with particles ranging in size from grains of sand to boulders several meters across, all orbiting Saturn at speeds that vary with distance, according to Kepler's laws of orbital mechanics. Before Cassini, most of what science knew about Saturn came from brief encounters. Pioneer 11 flew past in 1979, Voyager 1 in 1980, Voyager 2 in 1981. These spacecraft crossed Saturn's neighborhood in days and moved on. They took photographs, recorded magnetic field data, measured particle environments, and left. The data they returned transformed understanding of the Saturnian system, but there was a fundamental limit to what a flyby could accomplish. A flyby captures a moment. It cannot follow a moon through seasons. It cannot watch a storm develop and dissipate. It cannot map a surface through repeated passes, cannot measure how a magnetic field changes over time, cannot trace the subtle gravitational signatures that reveal what lies beneath an opaque atmosphere. An orbiter can do all of that, but getting an orbiter to Saturn is not simple. Saturn is far, not just in the way that distant objects feel remote when seen from Earth, but in the physically demanding way that means a spacecraft launched from Earth cannot simply aim for the planet and accelerate toward it. The fuel required to do that directly, at any reasonable speed, would make the spacecraft impossibly heavy at launch. Instead, mission designers use gravity. They use the mass of other planets to do what rockets cannot. The trajectory that took Cassini to Saturn required 4 gravity assists: Venus twice, Earth once, and Jupiter once. The spacecraft launched in October 1997, flew past Venus in April 1998, swung back through the inner solar system, past Venus again in June 1999, flew past Earth in August 1999. Only 2 years after launch, it returned to the planet it had just left, using Earth's gravitational pull to gain the speed it needed, and then arced out to Jupiter, which provided the final boost in December 2000. Cassini arrived at Saturn in July 2004, 6 years and 9 months after it left Earth. The arrival was one of the most complex autonomous maneuvers ever attempted by a deep space mission. Saturn orbit insertion required the spacecraft to fire its main engine for 96 minutes while passing through Saturn's ring plane, a maneuver that had to work perfectly with no real-time human guidance possible because the signal travel time meant that any command sent from Earth would arrive 44 minutes too late to correct an error. The burn happened on the far side of Saturn, hidden from Earth's view. Engineers at JPL waited in silence for the signal confirming the spacecraft had survived. When it arrived, Cassini was in orbit. What followed was a mission designed to last 4 years. It lasted 13. The original Cassini mission ran from 2004 to 2008. Then the mission was extended. The Cassini Equinox mission, running through 2010, was designed to observe Saturn as it approached equinox, the moment when the sun passes directly over the planet's equatorial plane, illuminating the ring's edge on. Then the Cassini Solstice mission, running through 2017, designed to observe a complete Saturnian season. Saturn's year is approximately 29.5 Earth years, and Cassini would observe nearly half of it, watching how the planet and its moons changed as the sun moved from southern summer to northern summer. By 2017, the spacecraft had been in operation for nearly 20 years. It had executed more than 2 million commands. Its imaging cameras had captured more than 450,000 images. Its 12 scientific instruments had collectively gathered a dataset that would take scientists decades to fully analyze. Its radio tracking data had been used to measure Saturn's gravitational field with enough precision to constrain models of the planet's interior structure. Its magnetometer had detected the near-perfect alignment between Saturn's magnetic and rotational axes, a finding that, as of the mission's end, still had no accepted theoretical explanation. But Cassini's hydrazine fuel, used to power the attitude control thrusters in the main engine, was running low. The propellant that had guided the spacecraft through a billion-kilometer journey, through 700 flybys of Saturn's moons, through 22 final plunging orbits between the rings and the planet, was nearly gone. Mission designers estimated that sometime in late 2017, the reserves would fall below the minimum required to maintain reliable attitude control. A spacecraft that cannot control its attitude cannot point its antenna at Earth. A spacecraft that cannot point its antenna cannot transmit data. A spacecraft that transmits no data is, from a scientific standpoint, no longer a functioning instrument. And there was a more serious concern. Enceladus. In 2005, Cassini's instruments detected something that changed the mission and, in a real sense, changed the question of life in the solar system. The spacecraft flew through a plume of material erupting from the south pole of Saturn's 6th largest moon. The plume was not unexpected. Voyager had detected some anomaly in that region, but what Cassini found inside it was not what anyone had prepared for. The plume contained water vapor. It contained ice particles. It contained sodium chloride, table salt. It contained molecular hydrogen. It contained silica nanoparticles that could only form in liquid water in contact with rock at temperatures above 90 degrees Celsius. This meant that somewhere beneath Enceladus's ice shell, which covers the entire moon, giving it the highest reflectivity of any body in the solar system, there was a liquid water ocean in contact with a rocky seafloor, undergoing hydrothermal reactions, producing the chemical gradients that, on Earth, support entire ecosystems of life in the absence of sunlight. The geysers launching water from that ocean were visible from space, and Cassini had flown through them. Titan presented a different kind of concern. Saturn's largest moon has a thick nitrogen atmosphere, thicker than Earth's at the surface, with a surface pressure 1.5 times greater than sea level on Earth. Beneath that atmosphere, Cassini's radar had mapped lakes and seas of liquid methane and ethane near the North Pole. It had found river channels carved by methane rain. It had found dunes of organic material stretching hundreds of kilometers across equatorial plains. The Huygens probe, which had separated from Cassini and descended through Titan's atmosphere in January 2005, had measured complex organic chemistry in the air and on the surface. Titan is not a candidate for life as we understand it. Its surface temperature is -179 degrees Celsius. Too cold for liquid water, too cold for the biochemistry we know, but it is a laboratory for prebiotic chemistry. The same organic molecules that formed on Earth before life began may be forming on Titan right now, preserved in a state that Earth's geologic activity has long since erased. Both of these moons, Enceladus and Titan, were now classified as objects of significant astrobiological interest, and that classification created a problem. Cassini had not been sterilized to the standard required for contact with potentially habitable environments. The spacecraft had been built and launched in the 1990s, before Enceladus's ocean was known to exist, before the full extent of Titan's organic chemistry was understood. It carried terrestrial microorganisms, not intentionally, but inevitably. Every surface, every cable, every instrument housing that had been exposed to Earth's atmosphere before launch potentially carried bacterial spores or hardy microbial life capable of surviving the vacuum of space. If Cassini drifted out of control and impacted Enceladus, it might deliver Earth life to an ocean that had developed in complete isolation for billions of years. The same risk, in a different form, applied to Titan. This was not a theoretical concern that could be dismissed as unlikely. It was a quantifiable probability that would only increase as the spacecraft's fuel reserves declined and its trajectory became harder to control. The only way to guarantee Cassini would never contaminate these moons was to destroy it, deliberately, completely, in an environment that would reduce it to atoms. Saturn's atmosphere was the answer. A spacecraft entering Saturn's upper atmosphere at interplanetary velocities would experience aerodynamic forces sufficient to break it apart, followed by frictional heating sufficient to vaporize the fragments. Nothing would remain. The carbon and silicon and metal that made up Cassini's structure would become part of Saturn, mixed into the same hydrogen and helium that has surrounded the planet since the solar system formed. It would not pollute any moon, it would not drift into any sensitive region, It would simply cease to be a spacecraft and become, atomically, part of Saturn itself. The decision to end the mission this way was made by NASA's Cassini project scientists and reviewed by the Committee on Space Research's Planetary Protection Office. It was formalized in the mission planning documents as the spacecraft's final trajectory, a controlled atmospheric entry, steep enough to ensure the spacecraft would not bounce off the upper atmosphere, shallow enough to allow continued data transmission for as long as structurally possible. They called it a controlled deorbit. They called it a disposal. In the language of mission planning, those are the correct terms. But the people who worked on Cassini for 20 years had other words for it. The grand finale began on April 22, 2017, when Cassini made its final close flyby of Titan, designated T-125 in the mission catalog. The gravitational pull of Titan's mass acted on Cassini's trajectory with mathematical precision, bending its path inward, lowering its closest approach to Saturn from a point outside the rings to a point inside them. T-125 was not a scientific flyby in the traditional sense. It was an orbital mechanics maneuver. Titan did not need to be studied on that pass. Titan needed to push Cassini onto its final path. After T-125, Cassini was in an orbit that passed through the gap between Saturn's D-ring, the innermost faint ring, and the top of Saturn's atmosphere. No spacecraft had ever been in that corridor before. No model of the environment there had ever been tested against real measurements. Scientists knew the ring particle density was probably low, otherwise the rings would decay rapidly from drag, but probably was not certainly, and the first transit required Cassini to orient its main antenna dish forward, using it as a shield in case the particle flux was higher than expected. It was not. The gap was cleaner than models had predicted, and what Cassini found there, in 22 orbits through a region that had never been sampled before, was more scientifically valuable than the last several years of standard operations combined. The gravitational field data, gathered by tracking minute variations in the spacecraft's velocity through Doppler measurements, showed that Saturn's interior is not as simple as early models assumed. The planet has a region of stably stratified fluid, a fuzzy core, neither solid nor fully convective, that extends outward much farther than the compact rocky or icy core that planetary formation models had predicted. The mass distribution implied by the gravitational harmonics required a core that has been dissolving into the surrounding metallic hydrogen for billions of years, a process called core erosion that had been theorized but never confirmed. The magnetic field measurements, made at closer range than any previous Saturn observation, revealed that the near-perfect alignment between the magnetic and rotational axes within 1/10 of a degree is real and not an artifact of measurement geometry. This is profoundly unusual. Every other magnetized planet in the solar system has a significant tilt between its magnetic and rotational axes. Earth's is 11 degrees, Jupiter's is 10 degrees, Uranus's is 59 degrees. Saturn's near zero tilt violates the standard dynamo theory that explains planetary magnetic fields, which predicts that a perfectly aligned magnetic field cannot be stable. The mechanism that maintains Saturn's field, the deep engine of metallic hydrogen circulation that generates it, remains one of the unsolved problems of planetary science. In each of those 22 final orbits, Cassini passed through the ring gap at speeds exceeding 30 kilometers per second relative to Saturn, sampling the charged particle environment, measuring the mass influx from ring material, raining into the upper atmosphere, collecting data that would eventually support more than 700 scientific publications. The instruments ran continuously. The data was transmitted continuously, relay by relay, through the Deep Space Network stations in California, Spain, and Australia, to servers at JPL, to the laptops of scientists scattered across more than 20 countries. And through all of it, the fuel level dropped. The last Titan flyby, T-126, designated the mission's final gravitational maneuver, occurred on September 11, 2017. This was not for science, or rather it was for science, in the sense that the data collected was real and valuable. But its primary purpose was trajectory. T-126 was Titan's final act in Cassini's story, a gravitational nudge that adjusted the spacecraft's orbit one last time, lowering periapsis, the closest point of the orbit to Saturn, into the upper atmosphere itself. After T-126, there was no orbit. There was only a path that led, in 4 days, to Saturn's sky. The spacecraft knew nothing of this, of course. It had no awareness of what was happening, no capacity to anticipate or resist. Its computers executed commands that had been uploaded from Earth weeks earlier. Its instruments measured what they were told to measure. Its thrusters fired when commanded. It was, in every functional sense, a machine doing exactly what machines do, following instructions with extraordinary precision, right up until the moment it could no longer follow them. On September 14, 2017, at approximately 4 in the morning Pacific Daylight Time, the Cassini mission team at JPL uplinked the final command sequence to the spacecraft. The sequence had been written and verified and tested in simulation for months. It told Cassini exactly how to spend its last 18 hours, which instruments to operate, what data to collect, how to orient itself, when to transmit. The last command in the sequence was not a shutdown. There was no command to shut down. Cassini was told to keep transmitting, keep measuring, keep sending data for as long as it physically could. The rest would be determined by physics. Outside the windows of JPL's spaceflight operations facility, the night was quiet. California in September, warm and dry, the air carrying the particular stillness of a place where the season has been the same for months. Inside, the monitors showed telemetry that was 83 minutes old, the time it took for Cassini's signal to travel from Saturn to Earth at the speed of light. Everything on those screens had already happened. The spacecraft whose data they were reading was already, at that moment, deeper into Saturn's gravitational field than any measurement could confirm in real time. The gap between event and knowledge, the gap that defines all deep space exploration. The universe does not accommodate impatience, and light, for all its speed, requires time. 83 minutes, 498 seconds. The span of time between what Cassini was doing and what the people watching its telemetry could know about it. In those 83 minutes, the spacecraft traveled more than 2.5 million kilometers. It crossed distances that would take a commercial aircraft years to cover. It moved through space so empty that the particle density around it was lower than the best vacuum achievable in any laboratory on Earth. And it was falling. Not dramatically, not visibly. The trajectory was a gentle arc by the standards of orbital mechanics, a slow descent toward a planet enormous enough that from Cassini's perspective, Saturn's gravity was just a persistent, patient pull, growing incrementally stronger with each passing hour. The upper atmosphere was still far below. The instruments were still measuring clean space, magnetic field lines, charged particle counts, dust impact rates so low that individual grains announced themselves as distinct events. But the arc was clear, the math was clear, and everyone who understood the math had known for months exactly where it led. September 15th, 2017 was going to be Cassini's last day. The morning of September 15th, 2017 began the same way every other morning at JPL's Spaceflight Operations Facility had begun for the past 13 years. Monitors glowing, telemetry scrolling, coffee cooling in paper cups beside keyboards that had transmitted commands across that same vast distance with the same basic protocols used to send an email. But the data arriving that morning was different in one specific way. For the first time in the mission, Cassini's accelerometers, the instruments that measure forces acting on the spacecraft's body, were showing non-zero readings that could not be attributed to thruster firings or mechanical operations aboard the spacecraft itself. The readings were small, fractions of a millimeter per second squared, but they were there, and they were increasing, and they had only one possible source: atmospheric drag. Cassini had entered the upper fringes of Saturn's atmosphere. The boundary between space and atmosphere is not a line, it is a gradient. The density of gas does not go from zero to something at a fixed altitude. It increases exponentially as altitude decreases, doubling approximately every 50 kilometers in Saturn's upper atmosphere. At the altitude Cassini first detected drag, the atmospheric density was still extraordinarily low, roughly equivalent to the environment 300 kilometers above Earth's surface, where the International Space Station orbits in a region so rarefied that it requires periodic reboosting to avoid orbital decay. But at Cassini's velocity, approximately 31 kilometers per second relative to Saturn, even molecules so sparse that they would constitute a near-perfect vacuum by any terrestrial standard produced a measurable force. The molecules were mostly hydrogen. Saturn's upper atmosphere, at the altitudes Cassini was entering, is composed of approximately 93% molecular hydrogen, with most of the remainder being helium and trace amounts of methane, ammonia, and water vapor. At these extreme altitudes, the hydrogen exists in an unusual state. The molecules are partially dissociated by ultraviolet radiation from the sun, creating a region called the thermosphere, where temperatures, counterintuitively, are higher than in the cloud layers far below. Cassini's instruments measured temperatures in this region exceeding 340 degrees Celsius, hot by human standards, though the low density means the thermal energy per unit volume is tiny, and heat transfer to the spacecraft structure was minimal compared to what was coming. The Ion and Neutral Mass Spectrometer, INMS, was collecting data in real time, sampling the molecular composition of the atmosphere as Cassini descended. This instrument had been designed specifically for atmospheric science. During the mission's earlier phases, it had analyzed the composition of Titan's atmosphere and flown through Enceladus's geysers, measuring the molecular weight of individual particles as they entered the instrument's aperture. Now it was doing what it had been built for in the most direct possible way, measuring Saturn itself. The data was extraordinary. In the upper atmosphere, NMS detected not only hydrogen and helium, but also complex organic molecules, compounds containing carbon, hydrogen, and nitrogen that had drifted upward from the deeper cloud layers or inward from the ring system. The rain of material from the rings into Saturn's upper atmosphere, a process scientists call ring rain, had been predicted theoretically but never measured directly until the grand finale orbits. Cassini's INMS data showed a flux of water, methane, ammonia, and complex organics falling from the ring plane into the atmosphere at a rate of several thousand kilograms per second across the entire planet, a number so large that, projected forward, it suggested Saturn's rings would be entirely consumed within 100 million years. 100 million years is not a long time, astronomically. The rings are estimated to be between 10 million and 100 million years old. Young by planetary standards, perhaps formed when a moon was broken apart by tidal forces or a collision, relatively recently in the solar system's history. If the current mass loss rate has been consistent, the rings may be a transient feature of Saturn's appearance, present for a blink of cosmic time on either side of the moment humans evolved to see them. This was one of the grand finale's most significant findings, and it came directly from the data Cassini was transmitting in its final hours. The magnetometer, MAG, continued measuring the magnetic field with increasing precision as Cassini descended closer to the planet. At these altitudes, the field was stronger than anything measured on previous orbits, and its structure revealed details that could not be detected from farther away. The instrument found evidence of magnetic field variations at small spatial scales, features that required electrical currents flowing in the upper atmosphere itself, currents driven by the differential rotation of atmospheric layers moving at different speeds. Saturn's atmosphere does not rotate as a rigid body. Different latitudes rotate at different rates, with the equatorial region rotating slightly faster than the higher latitudes, and this differential rotation generates shear forces and electrical currents that feed back into the planet's complex magnetic dynamics. These were final measurements, science that would appear in journals for years, data that would be cited in papers about atmospheric composition, about ring dynamics, about planetary magnetic field generation, papers written by researchers who were still graduate students in 2017, papers that have not yet been written, papers that will reference measurements made by an instrument that no longer exists. Cassini sent it all home. The telemetry stream was continuous, not because the spacecraft was laboring to transmit, quite the opposite. The radio system was operating normally, pointing its high-gain antenna at Earth with the same precision it had used for 13 years, generating a signal that crossed that same interplanetary gulf to reach a 70-meter dish antenna in Canberra, Australia, one of 3 Deep Space Network stations spaced roughly 120 degrees apart around Earth's longitude to ensure continuous coverage as the planet rotated. The signal strength was nominal, the data rate was nominal. From the perspective of the telemetry systems, this was an ordinary morning. Only the accelerometer data said otherwise, and as the minutes passed, the accelerometer readings climbed. At an altitude of approximately 1,500 kilometers above the visible cloud tops, the level of Saturn's atmosphere where pressure equals 1 bar, roughly equivalent to Earth's sea level, the atmosphere begins to take on what most people would recognize as atmosphere: clouds, weather, color, structure. Below that level, ammonia crystals form the white and yellow bands that give Saturn its pale, banded appearance. Below that, ammonium hydrosulfide clouds create a brownish layer. Below that, water ice clouds, and below them, water in liquid form, and below that, much deeper, at pressures that would crush any spacecraft ever built, the gradual transition from gas to liquid to the metallic hydrogen state that generates the planet's magnetic field. Cassini would never reach those depths. It would never reach the cloud tops. It would be destroyed long before it got there. But in the upper atmosphere, the data continued to flow. The composite infrared spectrometer, CRS, was measuring the thermal emission of the atmosphere, mapping temperature structure at different altitudes with wavelength-resolved precision. The ultraviolet imaging spectrograph, UVIS, was detecting the absorption signatures of atmospheric gases at ultraviolet wavelengths. The Radio and Plasma Wave Science Instrument, RPWS, was listening to the electromagnetic environment, detecting the radio emissions generated by lightning in Saturn's deep atmosphere, lightning that occurs in storms far below, in a region of water and ammonia clouds that Cassini would never reach, generating radio waves energetic enough to propagate upward through tens of thousands of kilometers of atmosphere and be detected by an instrument in the thermosphere. Saturn has lightning. It produces radio bursts measurable from Earth's orbit, bursts far more powerful than terrestrial lightning by a factor of 10,000 or more, generated in storm systems that can persist for months and circle the entire planet. The Great White Spot, a class of periodic storm that erupts in Saturn's northern hemisphere roughly every Saturnian year, approximately every 30 Earth years, had appeared in 2010 and been extensively studied by Cassini. The storm's lightning had been some of the most powerful ever detected in the solar system. RPWS had recorded it in detail. Now, RPWS was recording the quieter electrical environment of the upper atmosphere, the persistent radio background of a planet going about its business, unaware that a machine was falling through its outer reaches for the first and last time. Cassini's attitude control thrusters fired intermittently, maintaining the spacecraft's orientation. This was critical. The high-gain antenna had to remain pointed at Earth, a disk of metal 2 meters across, aimed at a planet that, from Saturn's distance, subtended less than 1/100th of a degree of sky. A deviation of a fraction of a degree would cause the signal to miss Earth entirely. The thrusters, burning hydrazine in small controlled bursts, corrected for any perturbation in the spacecraft's attitude. Tiny disturbances from solar radiation pressure, from the uneven drag of the atmosphere on the spacecraft's asymmetric body, from the electromagnetic forces of the magnetic field acting on the spacecraft's electrically charged surfaces. Each thruster firing consumed fuel. The fuel was running out. The mission had been designed so that the last firing of Cassini's thrusters would occur in Saturn's atmosphere. The spacecraft would keep itself pointed at Earth for as long as the thrusters had enough propellant to overcome the aerodynamic torques. When the propellant was gone, or when the torques exceeded the thruster's maximum force, the antenna would begin to drift off Earth. The signal would weaken, and then it would be gone. This was not failure. This was the mission ending exactly as designed. In Pasadena, it was the evening of September 14th. The team that had gathered in the spaceflight operations facility was not large. Most of the mission scientists were watching from offices or homes, following the telemetry through laptop screens, or were simply asleep, having scheduled themselves to be awake for the final minutes of signal. The core operations team on console had worked through the night. They had uploaded the final command sequence. They had verified the spacecraft's trajectory. They had confirmed the data transmission rate. There was nothing left to do but watch the telemetry and wait for the 83-minute delayed window into what was already happening at Saturn. The Deep Space Network's Canberra station was the primary receiving station for the final transmission, chosen because of its geometry relative to Saturn's position in the sky that morning. The 70-meter dish, designated DSS-43, the largest steerable antenna in the southern hemisphere, had been tracking Cassini for days. Its receivers were calibrated to the spacecraft's frequency. Its processors were recording every bit of data that arrived. Somewhere in that data, in the frequency shifts of the carrier wave, as Cassini's velocity changed under Saturn's gravity, was information about the planet's gravitational field. Somewhere in the spectral analysis of the signal's polarization was information about the magnetic field. The physics of the transmission itself was a measurement. The universe is like that. Information is encoded in everything. The way a signal travels, the way it shifts, the way it arrives, all of it tells a story about the space and gravity and magnetic fields it passed through on its way to the receiver. Cassini was not just transmitting data, it was being observed. Its own passage through Saturn's gravity was a measurement of Saturn. The team at JPL knew approximately when the signal would stop. They had calculated the entry trajectory, modeled the atmospheric density, estimated the aerodynamic forces, projected the thruster performance. The math said the spacecraft would lose attitude control somewhere in the upper atmosphere at an altitude of approximately 1,500 kilometers above the 1 bar pressure level between 11 and 12 hours UTC on September 15th. But math is a model. Saturn's atmosphere is a reality, and reality always has more detail than the model includes. The actual moment of signal loss would be determined by the exact atmospheric density profile at Cassini's entry point, at that specific latitude, at that specific local time of day on Saturn, in conditions that had never been directly measured at that location. The model was good, the estimate was reliable, but there was uncertainty in the final minutes that no amount of preparation could eliminate. This is the fundamental nature of exploration. The mission team did the math, built the model, prepared for every scenario the models could anticipate, and then encountered what only reality could reveal. The spacecraft was falling, the atmosphere was thickening, the thrusters were firing more frequently as the drag increased. The data was still flowing. In Canberra, the dish tracked Saturn's position across the southern sky. The signal it was receiving had left Saturn 83 minutes ago. The events it described were already history. And in 83 minutes, the next chapter of that history would arrive. Or it would not, because the signal would already be gone. The Earth turned. The sun rose over Australia. The dish tracked. And in the silence between Saturn and Earth, in 1.4 billion kilometers of almost perfect nothing, a signal made of light was crossing the distance at the only speed anything can move across that void. 300,000 kilometers per second, and still 83 minutes. The story of those 83 minutes was already written. It was just traveling. The history of Cassini's final transmission is, in one sense, a story about signal, but it is also a story about what it means to build something and send it away. When Cassini launched in October 1997, it carried instruments that represented the combined scientific ambitions of scientists in 17 countries. The spacecraft itself had been assembled at JPL in Pasadena over a period of years, each component tested individually, tested in assembly, tested against the thermal and vibrational stresses of launch. The launch itself, a Titan IB/Centaur rocket lifting off from Cape Canaveral at 4:43 a.m. Eastern Time on October 15, 1997, was the end of one phase of the mission and the beginning of another. After launch, the team could not touch it. They could command it, monitor it, analyze its data, calculate corrections to its trajectory, but they could not physically reach it. Whatever they had built into it, whatever they had installed and calibrated and tested, that was what Cassini would have for the rest of its existence. Every instrument reading that arrived at JPL was a message from something that was, in physical terms, entirely beyond reach. This defines all deep space exploration, but it takes on a particular quality in the final hours of a mission. The spacecraft is still there. It is still functioning. It is still transmitting, but the distance that has always separated it from human hands has not changed. The only thing that has changed is that it is about to stop. The Cassini mission team included people who had spent the majority of their professional careers on a single spacecraft, scientists who had designed instruments in the late 1980s and early 1990s, when the mission was still in its planning phases, when Saturn was decades away, when the word Enceladus referred to a moon nobody had found geysers on yet, who were now watching the end of the thing they had built. Engineers who knew the electrical schematics of systems that no longer existed anywhere on Earth, the original blueprints in archives, but the components themselves burned up or recycled long ago, who carried in their memory a detailed picture of a machine that was, at this moment, falling through an atmosphere at planetary distance. There is a particular quality to the knowledge that something will end at a known time. Not the surprise of failure, not the slow drift of obsolescence. A fixed point, calculated and confirmed and approached on schedule, with the hours counting down in both directions simultaneously, backward toward the 20 years that preceded it, forward toward the moment of silence. The spacecraft had been alone for all of that time, in the most complete sense of alone that exists, separated from any contact except radio waves, surrounded by vacuum, heated on one side by sunlight, attenuated to a fraction of its Earth intensity, cooled on the other side by a sky whose temperature is 2.7 degrees above absolute zero. Cassini had experienced this solitude for nearly 7,000 days. It had maintained its instruments, managed its power, executed its commands, reported its findings, all in a silence broken only by the pulses of radio that crossed the void in both directions, carrying instructions one way and data the other. Now the data was Saturn itself. The ENMS instrument was measuring the atmosphere at altitudes no other measurement had ever reached. The results were being processed in real time by onboard systems and formatted for transmission. The data rate was approximately 142 kilobits per second, a rate that, by terrestrial standards, is slower than a typical home internet connection, but which, considered as a transmission across 1.5 billion kilometers from a spacecraft with a nuclear power source producing less electricity than a household refrigerator, is a remarkable technical achievement. Each kilobit contained real science, molecular abundances accurate to parts per billion, temperature measurements precise to a fraction of a degree, magnetic field vectors resolved to tiny fractions of a nanotesla. These numbers, scrolling across the monitors at JPL 83 minutes late, represented the deepest atmospheric measurements ever made of any gas giant planet. They were unprecedented. They would not be repeated for decades until some future mission reached Saturn and carried its own instruments into the planet's thermosphere. The atmosphere thickened, the drag increased, the accelerometers climbed. Cassini's attitude control system, a set of reaction wheels backed up by thruster systems, continued to work. The reaction wheels, spinning flywheels that transfer angular momentum to the spacecraft to change its orientation without expending propellant, had been the primary attitude control method throughout the mission. But in the increasing aerodynamic environment of atmospheric entry, the torques exceeded what the reaction wheels could manage alone. The thrusters supplemented them. Each thruster was a small nozzle, a few centimeters in diameter, burning catalytically decomposed hydrazine to produce thrust measured in newtons, comparable to the weight of a large apple. Individually, the force was tiny, but applied at the right location on a spacecraft whose moment of inertia was precisely known, these tiny forces were sufficient to counteract the atmospheric drag trying to tumble the vehicle. In, out. The thrusters fired, the antenna held its aim, the data flowed. The physics of what was happening to Cassini's structure was governed by the same equations that govern any object moving through a fluid. Drag force equals 1/2 times atmospheric density times the square of velocity times drag coefficient times reference area. At Cassini's velocity of 31 kilometers per second, even the extraordinarily low density of Saturn's upper thermosphere produced significant drag. As the spacecraft descended, density increased exponentially. Drag increased with it. The aluminum and titanium of Cassini's bus, the central structure that housed its computers, power systems, and fuel tanks, was built for the cold vacuum of interplanetary space, calibrated for launch loads and radiation. Aerodynamic heating at hypersonic velocity was outside its design envelope entirely. At hypersonic velocities in an atmosphere, the compression of air ahead of the spacecraft creates a bow shock, a region of superheated gas where the kinetic energy of the spacecraft's motion is converted into thermal energy. On Earth, the space shuttle experienced bow shock temperatures of approximately 1600 degrees Celsius during re-entry. Cassini, moving faster through a denser than predicted lower thermosphere, would experience something comparable. But that was still ahead. The signal was still transmitting. The Canberra dish held its lock. The telemetry continued. Outside the operations facility windows, the California night was giving way to a gray morning. It was nearly 6 a.m. Pacific time. The engineers on console were watching numbers that described events that had already concluded at Saturn. Somewhere in that scrolling data was the last measurement Cassini's INMS would ever make. Somewhere in the magnetic field readings was the deepest field measurement the MAG instrument would ever record. The spacecraft was still transmitting, but the data being received right now, this data, these numbers on these screens at this moment, was data from 83 minutes ago, when Cassini was still intact. The question of what was happening at Saturn right now was unanswerable. It would remain unanswerable for another 83 minutes. This is the condition of knowledge at planetary distances. Not ignorance. The physics was known, the trajectory was calculated, the atmospheric models were good, but knowledge is not the same as certainty, and certainty is not the same as presence. The team at JPL knew what was happening at Saturn in the same way a letter writer knows what a letter will say after it has been sent. The content is fixed, the outcome is determined, but the reading of it must wait for the light to carry the words across the distance. The light was carrying the words 300,000 kilometers per second, across 1.5 billion kilometers of solar wind and cosmic ray flux and the near absolute cold of the interplanetary medium, past the asteroid belt, past Jupiter's distant presence, past the orbits of the inner planets, inward through the decreasing distance to Earth, through the ionosphere, through the atmosphere, down to a receiver in Canberra that was waiting with the patience of technology. Patient because it had no capacity for impatience, patient because it simply worked. Cycle after cycle, tracking and receiving and recording, as it had been doing for decades. In, out, the last of the data, the last of the signal. And somewhere at Saturn 83 minutes ago, Cassini was still falling. The clouds far below, the ammonia crystal layers, the yellow bands visible from Earth, were still hundreds of kilometers deeper than the spacecraft had reached. Between Cassini and those clouds was a column of gas growing steadily denser, and Cassini was moving into it at 31 kilometers per second, and the thrusters were firing, and the instruments were measuring, and the antenna was aimed at a blue dot in the distant sky that the spacecraft systems could not see but could calculate with perfect precision. The last thing Cassini would ever do was aim itself at home. The altitude was decreasing at a rate that the onboard systems did not evaluate and did not resist. Cassini had no programming to pull itself up, no instruction to slow down, no command sequence that would trigger any response to the growing density of the atmosphere pressing against its structure. It had been told to do exactly what it was doing: descend, measure, transmit. The only authority over its trajectory at this point was Saturn's gravity, which does not negotiate. At an altitude of approximately 1,200 kilometers above Saturn's 1 bar pressure level, the atmospheric density had reached a value equivalent to the environment roughly 200 kilometers above Earth's surface. Still extraordinarily thin by any terrestrial standard, but thick enough that Cassini's body was beginning to experience a continuous aerodynamic load rather than the occasional molecular impact of deep space. The difference is not simply quantitative. In deep space, individual molecules strike the spacecraft at random, producing statistical effects averaged over time. In an atmosphere, even a thin one, the flow is continuous, a stream rather than a hail, with structure and directionality, imposing forces that have preferred axes relative to the spacecraft's shape. Cassini was not designed as an aerodynamic vehicle. Its shape was determined by the requirements of science and engineering: a cylindrical main bus, a large dish antenna mounted on one end, instrument booms extending outward, a magnetometer boom nearly 11 meters long, radioisotope thermoelectric generators mounted on struts to keep their radiation away from the sensitive instruments. From an aerodynamicist's perspective, it was a poor shape for moving through atmosphere, irregular, asymmetric, with projections that would catch the flow unevenly and generate torques trying to tumble the vehicle. This was exactly the challenge that the attitude control system was now managing in real time. The reaction wheels, 3 primary and 1 backup, spinning flywheels oriented along orthogonal axes, had been handling attitude control since early in the mission. Their principle of operation follows directly from the conservation of angular momentum. If the spacecraft spins one wheel faster in one direction, the spacecraft's body must rotate in the opposite direction to conserve the total angular momentum of the system. They had no moving parts in contact with each other, no friction-limited lifetime in the traditional sense, and they required no propellant. They were, in the benign environment of deep space, nearly ideal. In an atmosphere, they were insufficient alone, The aerodynamic torques, forces trying to rotate the spacecraft away from its intended orientation, exceeded the authority of the reaction wheels. The thrusters supplemented them, firing in coordinated bursts measured in milliseconds, each burst consuming a small quantity of the remaining hydrazine. The control system that managed this was running a continuous loop: measure attitude, compare to desired attitude, calculate required correction, fire thrusters, measure again. The loop repeated hundreds of times per second. It had been running continuously since launch, but never against forces like these. The hydrazine remaining in Cassini's tanks at this point was measured in kilograms. The exact amount was not precisely known. Propellant gauging in zero gravity is an inherently uncertain measurement, and the mission team had been working with estimated values for months. What was known was that it was enough to continue for some time longer. How long depended on how hard the atmosphere pushed, and how hard the atmosphere pushed depended on the density at each successive altitude, and the density was being measured for the first time by instruments on the very spacecraft that would be destroyed by it. This is the strange recursive condition of final atmospheric entry. The spacecraft is simultaneously the measuring instrument and the thing being measured against. Every data point the INMS recorded about atmospheric density at that altitude was also a data point about the forces that were consuming the fuel that was keeping the antenna pointed at Earth. The ion and neutral mass spectrometer was operating at its maximum sensitivity. At these altitudes, the molecules entering its aperture were sparse enough that individual detections were statistically meaningful. Each count represented a real molecule, not background noise. The instrument had been designed with enough dynamic range to operate usefully across many orders of magnitude of atmospheric density, from the near vacuum of the upper thermosphere to the denser middle atmosphere. It would continue operating and transmitting data until the spacecraft lost attitude control and the antenna drifted off Earth. What it found in those final measurements would take years to fully analyze. The ratio of hydrogen isotopes, regular hydrogen versus deuterium, the heavier form with a neutron added to the nucleus, in Saturn's upper atmosphere differs from the ratio in the solar wind and from the ratio in the outer solar system's ice-rich bodies. This isotopic signature is a record of the material that formed Saturn and the processes that have modified it over 4.5 billion years. The ratio measured by INMS in these final passes carries information about where Saturn's water came from, about the mixing of material in the early solar system, about the relative contributions of different source populations to the composition of the gas giants. This single measurement, a ratio of two numbers, encodes the history of the solar system. Altitude 900 kilometers above the 1 bar level. The drag was now significant enough that the spacecraft's trajectory was being measurably altered, not dramatically. The entry angle was shallow enough that a single pass through the atmosphere would not have been enough to capture Cassini without the gravitational constraint imposed by T-126. It would have swept through the upper atmosphere and continued into space. But T-126 had done its work. The trajectory was bound. Gravity was patient. The atmosphere was patient. They had all the time the physics required. In Pasadena, it was 6:31 a.m. Pacific Daylight Time. The telemetry screens showed data from 5:08 a.m., 83 minutes earlier. The spacecraft that had generated that data was at this moment somewhere in Saturn's atmosphere, at a location the team could calculate but not observe. The calculations said it was still intact. The calculations said the antenna was still pointed at Earth. The calculations said the signal currently crossing the solar system had been generated approximately 40 minutes ago in Earth-Elapsed time and would arrive at Canberra in approximately 43 minutes. Earl Mays, the Cassini program manager, was in the operations facility. He had been with the mission since the early 2000s. Linda Spilker, the project scientist, was present. Diane Sumner, the Cassini mission manager, was there. Dozens of engineers and scientists who had built instruments, written software, designed trajectories, analyzed data, people whose careers had been shaped by a spacecraft that was, at this moment, being dismantled by physics in the upper atmosphere of a planet nearly 1.5 billion kilometers away. There was not much to say. The work was done, every command had been sent. Every trajectory had been calculated, every instrument had been activated. The decisions that could be made had been made months and years earlier in meetings and analyses and review panels that had run through every scenario, questioned every assumption, and arrived at a plan that was now executing itself without any further input required from anyone in that room. The universe was doing the rest. At Saturn, the numbers were changing faster now. The accelerometer readings, the measure of non-gravitational forces on the spacecraft, were climbing steadily. The aerodynamic load had increased to the point where the attitude control system was devoting most of its authority to maintaining orientation. The thrusters were firing more frequently in longer bursts. The hydrazine consumption rate had increased. The control system was still maintaining lock. The antenna held its position. Telemetry continued across the void. But the margin was narrowing. Between the spacecraft's maximum thruster authority and the aerodynamic torque acting on its structure, there was a gap, the control margin, and that gap was closing. It had been calculated. The mission team knew approximately when it would reach zero. Zero meant the thrusters could no longer maintain the antenna's pointing. Zero meant the signal would begin to drift. And once it began to drift, at the rates now involved, it would be gone within seconds. The last data transmitted by Cassini would not be marked as last. There would be no special packet, no end of transmission code, no farewell message embedded in the telemetry stream. The data would simply stop. One moment there would be numbers, atmospheric density, magnetic field strength, temperature, ion counts, and the next moment there would be noise. The transition would be abrupt, the consequence of physics, as final and unambiguous as anything in the natural world. Altitude 700 kilometers, the atmospheric density had increased by a factor of several hundred since the first faint drag signals appeared. The gas surrounding the spacecraft was still far too thin to see, to feel, to register by any human sense, but to instruments calibrated for the measurements of deep space, it was an environment of considerable complexity. Hydrogen and helium dominated, but traces of methane, ammonia, water vapor, phosphine, and the complex organic molecules raining in from the rings were present at levels that ENMS could detect and measure. Phosphine, a compound of phosphorus and 3 hydrogen atoms, should not exist in Saturn's upper atmosphere in the quantities observed. Phosphine is thermochemically unstable at low pressures and temperatures. It should be oxidized and destroyed long before it reaches the altitudes where Cassini was detecting it. Its presence implied that something was transporting it upward from the deep interior, faster than chemistry could destroy it. Convective mixing, perhaps, driven by heat from Saturn's interior, carrying material from the high-pressure depths where phosphine is thermodynamically stable into the cool upper atmosphere where it is not. This was not an idle curiosity. The same question, why does phosphine appear in the upper atmosphere of gas giants, would become the center of one of the most discussed scientific controversies of the following years, when a 2020 paper claimed to detect phosphine in the atmosphere of Venus and suggested biological production as a possible explanation. The Cassini measurements of Saturn's phosphine, gathered in these final hours, provided context for that debate. Science does not end when a mission ends. It continues in the papers, the data sets, the questions that the data raises, and that future missions or observations will answer. Cassini's last measurements were still generating science years after the spacecraft ceased to exist. Altitude 500 kilometers. The thrusters were firing almost continuously now. The control system was executing what engineers call limit cycling, oscillating rapidly around the target orientation as the aerodynamic torques repeatedly pushed the spacecraft off pointing and the thrusters repeatedly corrected it. Each correction consumed propellant, each oscillation consumed time. The system was still working, but it was working at its limits, and the atmosphere was growing denser with every passing second. The structure of Cassini's body was experiencing something it had not experienced in the 13 years since launch: sustained mechanical stress from external forces. In deep space, the spacecraft's structure was loaded primarily by the thermal gradients between sunlit and shadowed surfaces, and by the small forces of thruster firings and attitude maneuvers. These were gentle loads well within the design margins. Now the aerodynamic pressure was adding a new load, not yet severe, not yet approaching structural limits, but present and increasing. The carbon fiber composite panels that made up parts of Cassini's structure were beginning to experience differential pressure across their surfaces. The aluminum alloy of the main bus was conducting heat from the warming leading surfaces to the cooler trailing ones. The instrument booms, designed to be rigid in the benign environment of space, were experiencing aerodynamic forces that their structural analysis had not been required to accommodate. None of this mattered to the science. The instruments were measuring. The data was transmitting. The structure was, for now, intact. At JPL, the clock read 7:54 a.m. Pacific Time. At Saturn, 83 minutes earlier, Cassini had been at approximately 450 kilometers above the 1 bar pressure level. The atmospheric density there, still far above the visible cloud tops, still in the tenuous upper atmosphere, was now dense enough to produce significant heating on Cassini's leading surfaces. Not yet catastrophic heating. Not yet the temperatures that would begin to degrade the spacecraft's structure. But the transition from negligible heating to significant heating is not a cliff, it is a slope, and the spacecraft was moving down it. The radio and plasma wave science instrument recorded something at this altitude that the mission had not anticipated: a clear signal of atmospheric lightning discharge, rising from the deep cloud layers below. Saturn's lightning, generated in water and ammonia cloud layers hundreds of kilometers deeper than Cassini's current position, produces radio bursts across a broad frequency spectrum. These bursts propagate upward through the atmosphere, and at the altitudes Cassini was now traversing, they were detectable with clarity that previous, more distant observations had not achieved. The discharge patterns carried information about the storm systems generating them. storm morphology, convective intensity, the electrical properties of the cloud layers. All of this was encoded in the timing and frequency structure of the lightning radio bursts. Cassini was recording it, transmitting it, sending it across the interplanetary medium to receivers that would store it, and scientists who would analyze it for years. In the final hours of its mission, still falling, Cassini was still doing science that had never been done before. The altitude decreased, the density increased, the drag increased. The thrusters fired. The pattern had a mathematical inevitability to it, each variable linked to the others by equations that were simple in form and absolute in consequence. Density as a function of altitude, drag as a function of density and velocity, propellant consumption as a function of drag, control authority as a function of propellant, signal duration as a function of control authority. The final variable in the chain, signal duration, was the one the people in Pasadena were watching. The telemetry on their screens was now from 7:12 a.m. Saturn time delayed, events from 83 minutes ago. The numbers were still nominal. The attitude control system was working. The high-gain antenna was locked. The science instruments were active and returning data. From everything on those screens, Cassini was functioning normally. But those screens showed the past, and the past at this point in the mission was the only comfort available. Altitude 300 kilometers above the 1-bar level. The atmospheric heating was now measurable by the spacecraft's thermal monitoring systems, sensors placed at key points on the structure to monitor temperature during operations that might generate heat. These sensors had been designed to watch for anomalous heating from electronic components, from the radioisotope thermoelectric generators, from thruster firings. Now they were detecting something from outside, the aerodynamic friction of hypersonic atmospheric entry beginning to warm the spacecraft's forward-facing surfaces. The temperature rise was still modest, tens of degrees above the nominal values for the spacecraft's sun-facing surfaces. The structure was well within its thermal design limits, but the trend was clear, and the physics was clear, and everyone who understood the numbers knew what the trend meant. At this altitude, moving at 31 kilometers per second, Cassini was experiencing deceleration forces of approximately 10 times Earth's surface gravity, 10 g. This is comparable to what a fighter pilot experiences in a hard turn, or what a race car driver experiences in a crash. The spacecraft was not designed for sustained loads of this magnitude. Its structure had been analyzed for launch loads, the violent, brief acceleration of a rocket lifting off, but not for the sustained aerodynamic battering of hypersonic atmospheric entry. The structure was beginning to be stressed in ways it had never been stressed before. And still the antenna held its bearing. And still the transmission reached across the distance. And still the camera dish tracked a point in the sky that corresponded to where Saturn had been 83 minutes ago, because light travels at a fixed speed, and the geometry of where a signal was sent and where it arrives are separated by the time light needs to cross the distance. And so every radio telescope, every deep space receiver tracks not where a planet is, but where it was when the signal left it. Tracking the past, receiving messages from something that, by the time the message arrives, has already moved on. In the final approach to signal loss, Cassini's telemetry showed something that the mission team would later describe as the most complete picture of any planet's upper atmosphere ever captured in real time. The instruments were performing exactly as designed, returning data at the maximum transmission rate, with all 12 science instruments active and contributing. The data quality was high. The signal-to-noise ratio was nominal by every technical metric except one, the hydrazine level in the attitude control tanks. This was a functioning spacecraft in the middle of a productive scientific observation. The exception was sufficient. At an altitude of approximately 1,500 kilometers, the point where atmospheric density had increased enough to generate thruster firing rates that the remaining fuel could no longer sustain indefinitely, the control margin reached its limit. Not zero, not quite. There was still fuel. There was still thruster authority, but the rate of consumption had exceeded the rate at which the mission's planning had projected it would at this altitude, because the atmospheric density was slightly higher than the models had predicted, because the real Saturn's atmosphere had more complexity than any model built from more distant observations could fully capture. The thrusters were firing at their maximum rate. The antenna held its lock. The transmission carried on. And then the aerodynamic torque exceeded the maximum corrective force the thrusters could apply. It did not happen suddenly. It happened the way most physical limits are reached, gradually, then all at once. The control system detected that the error between actual orientation and desired orientation was growing faster than the thrusters could correct. The error grew. The antenna began to drift, fractions of a degree, then degrees. The signal at Canberra began to weaken. Not because anything had broken, not because any instrument had failed. The signal weakened because the antenna generating it was no longer aimed precisely at Earth, and a high-gain antenna, focused like a spotlight, narrow by design, produces a signal that falls off sharply as pointing error increases. The carrier wave, the pure radio frequency tone that the receivers lock onto, began to fluctuate. The data modulated on top of it became harder to decode. The signal-to-noise ratio degraded. Bits were lost, then many bits, then the carrier itself became too weak to lock. At 11 hours, 55 minutes, and 46 seconds Coordinated Universal Time, September 15, 2017, the signal from Cassini vanished from the screens at JPL and from the data recorders at Canberra. The line went flat. The spacecraft that had left Earth 20 years earlier, that had traveled 6.7 billion kilometers to reach Saturn, that had completed 294 engine burns and 127 targeted moon flybys, that had discovered the geysers of Enceladus and mapped the lakes of Titan and threaded 22 times through a gap 2,400 kilometers wide between a planet's rings and its atmosphere. That spacecraft was gone. What happened to the structure after signal loss was determined entirely by physics. With attitude control lost, Cassini began to tumble. The aerodynamic forces that had been fighting the thrusters now acted unopposed on an irregularly shaped object moving at hypersonic velocity through a thickening atmosphere. The tumbling increased the effective cross-section of the spacecraft presented to the flow, which increased the drag, which increased the heating. The bow shock temperature ahead of the spacecraft rose rapidly. Aluminum melts at 660 degrees Celsius. The bow shock temperature at Cassini's entry velocity exceeded that within seconds of uncontrolled tumbling. The aluminum panels of the spacecraft's bus began to soften, then deform, then ablate. the process by which material is removed by the combined effects of heating and aerodynamic shear, the same process that removes material from meteor surfaces as they enter Earth's atmosphere. The spacecraft that had been built in Pasadena, California in the early 1990s, assembled by engineers in clean rooms, tested in thermal vacuum chambers, carried to Cape Canaveral on a truck, became in the space of a few tens of seconds a rapidly expanding cloud of metallic vapor and fragmented solid material moving through Saturn's upper thermosphere at hypersonic speed. The cloud dispersed. Saturn's atmosphere mixed it upward and downward, east and west, distributing the atoms through the hydrogen and helium envelope of a planet 11 times Earth's diameter. The individual atoms, aluminum and titanium, and carbon and silicon and gold, from the multi-layer insulation, settled into the same statistical distribution that governed every other trace component in Saturn's atmosphere. The mass that had been Cassini distributed into Saturn's atmosphere represents approximately 1 part in 10 to the 17th power of the planet's total atmospheric mass. It is unmeasurable. It is indistinguishable from background. There is no instrument that could detect it, no observation that could localize it, no way to find it again. It is simply there, mixed into a planet, the way everything eventually mixes into everything else, given sufficient time and sufficient turbulence. And Saturn continued turning, 16 days, 5 hours, 55 minutes for one full rotation. Its rings continued orbiting, the inner edges moving faster than the outer edges, the differential velocities maintaining the sharp boundaries between ring regions that Cassini had spent years studying. Enceladus continued erupting its geysers from the South Pole, sending plumes of water 200 kilometers into space, the same plumes that Cassini had discovered, the same chemistry that had changed the mission's meaning. Titan continued its rain of liquid methane into rivers and lakes and methane seas. The dunes continued. The haze layers continued. The Huygens landing site, a plain of rounded ice pebbles, photographed for 94 minutes in January 2005 before the probe's batteries were exhausted, continued sitting under a nitrogen sky that nobody had looked at since. The universe did not stop for the loss of the instrument observing it. It never does. But the people in the room in Pasadena and the people watching from offices and homes across 20 countries, watching the telemetry screens go flat, marked the moment anyway. Not because the universe required marking, because they required it. The mission had ended, and the silence on the telemetry screens, which looked identical to any other silence, to any other gap in data, to any momentary loss of signal that had happened hundreds of times over 13 years for entirely recoverable reasons. That silence was different now. It was final. The last image Cassini had taken was a mosaic of Saturn's rings, assembled the day before entry to give scientists a final, high-resolution view of the structure that would not be imaged again at that resolution for decades. The last atmospheric data it had collected was being processed at JPL and distributed to the science teams. The last magnetic field measurement was already in the data archive. The instruments were gone, the data remained. And in the data, more science than any one scientist could analyze in a lifetime. More questions than the mission had answered. More evidence about the formation of Saturn, the dynamics of its rings, the chemistry of its moons, the interior structure of gas giants, the history of the outer solar system. more of all of it than had existed before Cassini arrived. This is what a mission leaves behind, not the hardware, not the spacecraft. The understanding. Outside the spaceflight operations facility, the California morning continued, as California mornings do. Warm, dry, the sky the pale blue of low humidity, traffic building on the freeways, the San Gabriel Mountains clear to the east. The world was indifferent to what had just happened in the room, as the world is indifferent to most things that happen in rooms. Science is like that. The discoveries are made in rooms, by people in front of screens, and the universe is changed in those rooms, and the world mostly does not notice. The team began the work of closing out the mission. Instruments were formally powered down in software. Though there were no instruments to power down, the spacecraft was gone. Data archiving procedures were initiated. The Deep Space Network assets that had been dedicated to Cassini were reassigned to other missions. The rooms that had been the nerve center of a mission to Saturn were cleaned up. The monitors switched to other spacecraft, other telemetry streams, other signals arriving from other machines in other parts of the solar system. The work of science does not stop when a mission ends. It shifts. The Cassini data, the complete archive of measurements from 12 instruments across 13 years of continuous operation, was accessible to any scientist with the credentials and the curiosity to use it. Papers were already written. Papers were being written. Papers would be written for years by people who would mine the data set for signals they had not known to look for when the mission was active, applying analysis techniques developed after the mission ended to data that recorded phenomena not yet understood when the data was collected. This is the second life of a mission. The first life is the mission itself, the operations, the real-time discoveries, the press releases, the flyby images released to the public within hours of collection. The second life is quieter, longer, and in many ways more scientifically productive. The systematic analysis of a complete data set by a community of researchers with the time to ask deep questions and the tools to answer them. Cassini's second life would last decades. It was already underway. The data archive at the Planetary Data System, the NASA repository where all planetary mission data is stored and made publicly accessible, received Cassini's final datasets within hours of the mission's end. The archive already contained decades of Cassini observations. The final edition was, in file size terms, modest, a few gigabytes from the grand finale observations and the final atmospheric entry. But in scientific terms, it was among the most valuable data in the archive. Measurements made at locations, altitudes, and conditions that had never been sampled before and would not be sampled again for the foreseeable future. Any researcher in the world with an internet connection could access it. This openness, the public availability of planetary mission data, is one of the less celebrated aspects of deep space exploration, but it matters enormously for the rate at which science advances. Cassini was not a closed project. Its data did not belong to the institutions that built it, or the agency that funded it in any proprietary sense. It belonged, in the practical meaning of that word, to anyone who wanted to use it. Graduate students in countries that had contributed nothing to the mission's construction could download the raw telemetry and write papers that would be published in journals read by the people who built the instruments. This happened. It kept happening. The papers accumulating in the scientific literature under the keyword Cassini grew steadily after the mission ended, not declining as the mission receded into the past, but continuing as researchers found new questions to ask of the existing data, new computational methods to apply, new theoretical frameworks that made previously incomprehensible measurements interpretable. The question of Saturn's ring age, whether the rings are a transient feature of the planet's appearance or a permanent structure that has existed since the solar system formed, had not been definitively answered at the mission's end. The data Cassini collected during the grand finale orbits constrained the answer. The ring mass, measured by gravitational analysis, implied a formation date between 10 million and 100 million years ago, well after the formation of the solar system 4.5 billion years ago. But the uncertainty in that estimate remained large enough that the question was not closed. Future analyses of the existing data and future missions that might carry instruments capable of different measurements would be needed to narrow it. This too is how science works. A mission does not answer all questions. It answers some, raises others, and constrains the space of possible answers to the ones it has not yet resolved. Progress is not the replacement of mystery with certainty, but the replacement of large mysteries with smaller, better defined ones. Saturn's rings were a smaller mystery after Cassini than they had been before, not no mystery, smaller. The same was true for the interior of Saturn. The gravitational field measurements from the grand finale orbits had revealed a fuzzy core, a region of inhomogeneous composition extending much farther from the planet's center than simple models had predicted. This implied that the core was not a compact solid body of rock and ice, but a diffuse region where core material had been mixing with the surrounding metallic hydrogen for billions of years, slowly dissolving outward in a process that changed the planet's interior structure on geological timescales. The theoretical implications of a dissolving core for planetary evolution models were still being worked out years after the mission ended. The magnetic field's perfect alignment remained unexplained. Standard dynamo theory, the set of physical principles that describes how the motion of electrically conducting fluid inside a planet generates and maintains a magnetic field, predicts that a stable magnetic field cannot be perfectly aligned with the rotation axis. The mechanism that produces alignment is the same mechanism that produces the field, differential rotation and convection in the conducting fluid. These processes tend to tilt the field away from the rotation axis. A field as closely aligned as Saturn's, within 1/10 of a degree, requires something that the standard theory does not include. Several explanations had been proposed. One involved a layer of helium rain, a phenomenon predicted by theory and confirmed by inference from Saturn's luminosity, in which helium droplets rain downward through the metallic hydrogen interior because helium becomes immiscible with hydrogen at high pressures. That might filter out the tilted components of the magnetic field as the field diffuses through it, leaving only the aligned component to emerge at the surface. This mechanism was theoretically plausible, but had not been confirmed, and the magnetic field data from Cassini's final orbits provided constraints that some proposed models could not satisfy. The problem remained open. It was a better defined open problem than before Cassini, but open. These unresolved questions were not failures of the mission, they were its legacy in the deepest sense. A mission that answered all questions would be a mission that had studied only easy questions. The Cassini mission had been ambitious enough to confront the hard ones, the interior structure of gas giants, the origin of ring systems, the conditions required for life in the outer solar system, the dynamics of complex moon systems, and had returned data of sufficient quality that the hard questions could be asked with much greater precision. The precision of the question is what determines the precision of the eventual answer. 453,048 images. This number appears in the mission's final statistics, and it resists full comprehension. Photographs of Saturn taken from orbit over 13 years. Images of the planet from every angle, in every filter, at every time of day and season. Images of the rings at resolutions sufficient to resolve individual ring structures 10 meters across. Images of Titan's surface through the haze, built up layer by layer from infrared wavelengths that penetrate what visible light cannot. Images of Enceladus's geysers, of Iapetus's equatorial ridge, of the propeller-shaped disturbances in Saturn's rings, created by embedded moonlets too small to be seen directly. Images of the hexagonal polar storm at Saturn's North Pole, a six-sided jet stream pattern with sides each approximately 13,800 kilometers long, larger than Earth's entire diameter, rotating with the same period as Saturn's radio emissions, its geometry stable and unexplained. Among those images, some had been released publicly within hours of downlink and had circulated widely. The image of Enceladus's plumes backlit by sunlight, white against the black of space, with Saturn's rings in the background. This image had appeared in textbooks, in magazine covers, on the walls of science museums. It had become one of the most widely reproduced images from any planetary mission. But most had been seen by very few people. Most existed in the archive as files with catalog numbers, waiting for the question that would make them useful, waiting for the researcher who would download them, process them, analyze them, and find in them something that nobody had known to look for. They were still waiting. The universe had not rushed to be understood. It was under no obligation to be understood. It continued, Saturn turning, Enceladus erupting, Titan raining methane into its lakes, the rings losing mass into Saturn's upper atmosphere at several thousand kilograms per second, the hexagonal storm rotating, the magnetic field threading through the metallic hydrogen interior and emerging into space in a configuration that no theory had yet explained, all of it continuing at the speeds and on the timescales that physics dictated, with complete indifference to whether anyone was watching. Cassini had watched for 13 years from inside the system. Now the watching fell to other instruments, more distant, Earth-based telescopes, space-based observatories, the occasional planetary spacecraft that passed through the outer solar system on its way somewhere else. None of them could match what Cassini had provided. None of them were in orbit. None of them could follow a moon through an entire year, sample a plume directly, fly through the ring gap, or measure the atmospheric composition from within the atmosphere itself. The gap left by Cassini's absence was real, and it was large. The next Saturn mission, if one flew, and as of the mission's end none had been formally approved, would take years to build, years to travel to Saturn, and would arrive to find a solar system changed in the ways that time always changes things. Rings a little thinner, orbital dynamics shifted by the long-term gravitational interactions of the moons, the geysers of Enceladus perhaps more active or less, depending on processes occurring in an ocean floor that no instrument had directly observed. Whatever a future mission would find, it would find a Saturn that had never been in contact with Cassini. The spacecraft was gone, its atoms were in the planet, the records it had made were in the archive. The questions it had raised were in the literature, waiting for the next instruments and the next minds to approach them. This is the full arc of a mission to a distant world. The spacecraft did not return. It became part of what it studied, leaving behind only data and questions, and the changed understanding of a species that, for one instrument lifetime, had a presence in the Saturnian system. The California morning continued outside JPL. The traffic on the Foothill Freeway moved at the speeds that traffic moved. The coffee in the operations facility was cold. The screens had shifted to other telemetry streams, other missions, other signals crossing other distances. And Saturn turned under its rings in the attenuated sunlight of the sixth orbit from a star, carrying in its upper atmosphere the atoms of the thing that had known it best. The concept of a spacecraft becoming part of a planet is not metaphor, it is chemistry. Cassini's structure was composed of materials chosen for their properties in the space environment: low mass, high strength, radiation resistance, thermal stability. The primary structural material was aluminum alloy, the same general class of material used in aircraft construction, but formulated for space applications. Titanium was used for components requiring higher strength to weight ratios, brackets, fasteners, propulsion system components. Carbon fiber composite panels provided structural rigidity in areas where aluminum's mass would be excessive. Gold-coated multi-layer insulation, dozens of alternating layers of aluminized mylar and dacron mesh, wrapped the spacecraft's exterior, managing the thermal environment by reflecting infrared radiation. All of this became, in the seconds following attitude control loss, an ablating mass in Saturn's thermosphere. The chemistry of ablation in a hydrogen-helium atmosphere differs from ablation in an oxygen-nitrogen atmosphere like Earth's. On Earth, the materials entering the atmosphere oxidize as they heat. Aluminum becomes aluminum oxide, carbon becomes carbon dioxide, titanium becomes titanium dioxide. In Saturn's atmosphere, the dominant reactive species is molecular hydrogen. Aluminum would react with hydrogen at high temperatures to form aluminum hydride. Carbon would form methane. The reaction products, themselves unstable at the temperatures and pressures involved, would further decompose and mix into the surrounding gas. The net result is that the atoms of Cassini, aluminum, titanium, carbon, silicon, gold, the various rare earth elements in the electronics, dispersed into a mixture that is 93% hydrogen and 7% helium, in which they represent trace level contamination far below the detection limit of any instrument ever built. They are still there. The atoms do not go away. They are mixed into the atmosphere, settling toward statistical equilibrium over timescales that depend on atmospheric dynamics, the same dynamics that Cassini was measuring in its final hours. Vertical mixing timescales in Saturn's upper atmosphere are measured in years to centuries for material at these altitudes. The atoms spread horizontally faster. Saturn's winds at high altitudes move at hundreds of meters per second in the zonal direction, carrying material around the planet in a matter of weeks. By now, the atoms that were once Cassini have been distributed around Saturn's entire atmospheric extent at the altitudes of entry. They are in the north and in the south. They are on the day side and the night side. They are in the bands that appear pale and in the bands that appear slightly darker, mixed according to the fluid dynamics of an atmosphere that has been circulating for 4.5 billion years. If Saturn has a future, and it does, a future measured in billions of years, during which the sun will slowly brighten, Saturn's rings will gradually disperse, and the moons will continue their long gravitational dance, then Cassini's atoms will participate in whatever that future holds. The aluminum that was once a spacecraft panel will be part of Saturn when the sun expands into a red giant. The carbon that was once a structural composite will be there when the outer solar system is reshaped by the dying star's mass loss. The gold from the insulation will be there. Gold is chemically inert enough to survive almost any environment, mixed into a planet for as long as the planet exists. This is a longer legacy than any human institution, longer than any nation, longer than the species that built the thing. Cassini will be part of Saturn for the remaining lifetime of the solar system. The data, meanwhile, has a different timescale. Data is only as permanent as the systems that preserve it, and those systems are human-made, subject to all the fragility that implies. The planetary data system archives are maintained by institutions that depend on funding, on infrastructure, on the continued existence of the organizations that support them. In principle, the data could be lost to funding cuts, to institutional collapse, to the simple degradation of storage media over decades. In practice, the scientific community has treated preservation of planetary mission data as a priority because the data, once lost, cannot be recovered. There is no way to fly Cassini again. There is no way to remeasure what it measured. The numbers in those archives are the only record of what Saturn's atmosphere was like in September 2017, at those altitudes, at that solar longitude, during that phase of Saturn's long seasonal cycle. If the data is lost, that knowledge is lost permanently. So the archives are maintained, formats are updated as technology changes, metadata is curated. Access is kept open. The humans who built Cassini will not live to see the end of the solar system. The data they collected will not either in all probability, but for the duration of the civilization that can maintain it. The archive holds a picture of Saturn as it was, measured by instruments that flew through its atmosphere and dissolved there, transmitted by radio waves that crossed the full width of the inner solar system at the speed of light, received by a dish in the southern hemisphere of a small rocky planet orbiting the same star that Saturn orbits, at the distance at which rocky planets can have liquid water on their surfaces. The distances involved are so large that they impose a certain perspective on the enterprise. Saturn is not close. Nothing in the outer solar system is close. The distances that define the solar system are not distances that human intuition, evolved in an environment of grasslands and forests and coastlines, measured in kilometers, can directly apprehend. They require mathematics. They require the willingness to trust a calculation rather than a sensation. Cassini crossed those distances. It took 6 years and 9 months to do it, flying a trajectory that spiraled outward through the inner solar system before swinging back and then far out to the orbit of Jupiter before the final approach to Saturn. The total path length was 6.7 billion kilometers. If that distance were driven at highway speed, 100 kilometers per hour, without stopping, it would take more than 7,000 years. In less than 7,000 years, writing was invented. Every human history that has ever been recorded happened in that time. Cassini covered that distance in less than 7 years. The speed of spacecraft is one of the ways in which the universe is more generous than intuition suggests. Physics permits fast things. The rocket equation, brutal in its requirements for propellant mass, is nevertheless consistent with trajectories that cross the solar system in years rather than millennia. And gravity assists, the elegant mechanism by which a spacecraft borrows velocity from a planet, gaining speed from the planet's orbital motion, while imposing an immeasurably tiny equal and opposite change on the planet itself, make those trajectories achievable with realistic amounts of propellant. Saturn lost an immeasurably tiny amount of orbital velocity when Cassini used it for gravitational assists on the way in, and again when Cassini entered orbit. The effect on Saturn is by any measure negligible, less than 1 atom's worth of change in a system containing more mass than the Earth contains atoms. But the effect on Cassini, the velocity gained, the trajectory achieved, the mission made possible, was everything. The universe permits this. It does not require it. Physics is not designed to be useful for spacecraft navigation. It simply is what it is, and what it is turns out to be consistent with a species on a small rocky planet sending a machine across 1 billion kilometers to study a ringed gas giant and its moons. This is what the data says, in aggregate, not just what Saturn is made of, or how its rings work, or whether Enceladus's ocean could support life. What the data says, across 635 gigabytes and 13 years of operation, is that the universe is knowable. That the same physics that governs a rocket engine governs a planet's gravity. That the same electromagnetic spectrum that lets a radio station broadcast music lets a spacecraft transmit atmospheric measurements from 1.5 billion kilometers away. That the same chemistry operating in a laboratory on Earth operates in the upper atmosphere of a gas giant in the outer solar system. Knowable, not known, knowable. The distinction matters. Science is not a record of what has been figured out. It is a practice of figuring out, ongoing, extending the boundary of the knowable outward into the unknown at a rate that depends on the instruments available and the questions being asked. Cassini extended that boundary by exactly as much as its data reveals, and no more. The questions beyond that boundary are waiting. The questions beyond that boundary are not abstractions, they have addresses. Enceladus is at a mean distance of 238,000 kilometers from Saturn's center, closer to Saturn than the Moon is to Earth, close enough that Saturn's tidal forces continuously flex and heat the Moon's interior, maintaining the liquid water ocean that exists beneath an ice shell, estimated to be between 5 and 20 kilometers thick. The ocean itself is estimated to be roughly 10 kilometers deep, comparable to the deepest parts of Earth's oceans, and sits above a rocky seafloor where hydrothermal venting has been confirmed by the presence of silica nanoparticles in the plume material that Cassini flew through. Silica nanoparticles of the type Cassini detected form under specific conditions: liquid water in contact with silicate rock at temperatures above 90 degrees Celsius, at pH levels between 8 and 10, mildly alkaline, similar to the conditions found at some hydrothermal vent systems on Earth's ocean floor. On Earth, those vent systems, fields of superheated water emerging from cracks in the seafloor, rich in chemical gradients between hot-reducing fluids and cooler, oxidizing ocean water, support entire ecosystems: tube worms, shrimp, crabs, microbial mats, communities of life that derive their energy not from sunlight, which does not penetrate to the deep ocean floor, but from the chemical energy of hydrothermal reactions. The same chemical gradients exist on Enceladus. The molecular hydrogen detected in the Enceladus plumes is a direct product of hydrothermal reactions between water and rock, specifically the process called serpentinization, in which water reacts with iron and magnesium-bearing silicate minerals to produce hydrogen gas, heat, and altered minerals. On Earth, serpentinization supports microbial communities in deep subsurface environments far from sunlight and far from the oxygenated surface ocean. The microorganisms that use this process, methanogens, which consume hydrogen and carbon dioxide to produce methane, are among the most ancient lineages of life on Earth and are found in environments that resemble in key chemical ways what Cassini detected at Enceladus. This is not proof of life on Enceladus. It is evidence that the chemical conditions for a specific type of life found on Earth exist on Enceladus. Whether that is sufficient, whether chemistry alone produces life, or whether life requires something more, is a question that biology and astrobiology have not yet answered and may not be able to answer without actually looking. Looking requires a mission. The mission that has been proposed, developed, and as of 2023 selected for development by NASA is called Enceladus Orbilander. It would do what Cassini could not merely fly through the plumes, but orbit Enceladus closely enough to make detailed measurements of plume composition and eventually land on the surface to directly sample material ejected from the ocean below. The science questions it would address are straightforward in concept, though difficult in execution. Are there organic molecules in the plumes consistent with biological origin? Are there cellular structures? Is the chemistry of the plume material consistent with a living system or with purely abiotic processes? These questions have answers. The answers exist right now in the chemistry of a small moon orbiting Saturn. The answers are present in the water vapor and ice particles rising 200 kilometers above Enceladus's south pole in continuous plumes that have been erupting for at least the duration of any human observation, probably for much longer. Cassini found the plumes. It characterized their chemistry in broad terms. It established that the conditions for life exist there. What it could not do, what no mission has yet done, is answer the question the plumes raise. That question is the most significant one in all of modern planetary science, and possibly in all of science. Is life on Earth an accident of this particular planet, or is it a consequence of physics and chemistry that arise wherever the right conditions exist? Cassini did not answer that question. It made the question precise enough to be asked with instruments rather than only with philosophy. This is a particular kind of scientific contribution, and it is undervalued in the public accounting of what missions accomplish. The discovery of the geysers of Enceladus is celebrated as a discovery because it is a discovery, something that was not known before and is now known. But the question that discovery implies, the question of life in that ocean, is the more consequential contribution because it redirects the attention of an entire field toward a specific, answerable target. Before Cassini, the search for extraterrestrial life was largely focused on Mars, for historical reasons having to do with the telescopic observations of the 19th century and the surface missions of the 1970s. Mars has water, or had it, and the presence of water in its past makes it a plausible candidate for ancient life. But Mars's surface is now dry, irradiated, oxidizing, not a place where life could easily persist today. Finding life on Mars, if it exists, would mean finding it underground, in subsurface water that may or may not exist and may or may not be accessible. Enceladus's ocean is not underground in the sense of being difficult to access. It is actively ejecting material into space. A spacecraft flying through the plumes is, in a real sense, sampling the ocean, receiving material that was, until recently, in contact with the seafloor of an extraterrestrial ocean. Cassini did this repeatedly. A future mission with more capable instruments could do it more thoroughly. The path from Cassini's discovery to the answer to the question of life in Enceladus's ocean is a path measured in decades of mission development, budget cycles, technical challenges, and the patient accumulation of scientific consensus. It is not a short path, but it is a path. Before Cassini, there was no such path. There was only the question of whether anything interesting existed in Saturn's moon system, a question that could be answered with varying degrees of optimism or pessimism, but could not yet be answered with data. Now there is data. Now there is a path. Titan is a different kind of target, with a different kind of question. The Dragonfly mission, a rotorcraft lander designed to fly through Titan's thick atmosphere and land at multiple locations on its surface, was selected by NASA for development in 2019 and is currently scheduled for launch in the late 2020s. It would land on Titan and use a nuclear-powered helicopter design to traverse the surface, visiting sites of scientific interest separated by distances of several kilometers per flight. On Earth, such distances would require roads or trails. On Titan, with its low surface gravity, 1/7 of Earth's, and its dense nitrogen atmosphere, 4 times denser than Earth's at the surface, which provides substantial lift even for a relatively small rotor system, a helicopter is a practical vehicle. Dragonfly would visit sites including the Selk impact crater, where the energy of a meteorite impact would have melted the surface ice and mixed it with organic material from Titan's dune fields, creating transient liquid water environments that might have persisted for thousands of years, long enough, possibly, for prebiotic chemistry to occur. The crater's preserved chemistry might record what happened when water and organics mixed in a place that is otherwise far too cold for liquid water to exist. This is Titan's scientific value as a target, not the possibility of current life, but the possibility of preserved prebiotic chemistry, the chemistry that preceded life on Earth, long since erased by Earth's geological activity, but potentially preserved on Titan, in the deep cold where chemistry proceeds so slowly that billion-year-old reactions might still be detectably in progress. Cassini established that this chemistry is rich and complex. The instruments that flew through Titan's atmosphere detected nitriles, tholins, complex organic aerosols, molecules of a type and complexity that had not been detected in any other planetary atmosphere. The Huygens probe measured the surface composition and found a landscape covered in organic material of a type that, on Earth, would be the product of billions of years of biological activity. On Titan, it is abiotic, made without life, from the same raw materials that life on Earth would later use. Dragonfly will land in this landscape and analyze it directly. The data Cassini gathered about Titan's surface and atmosphere will guide Dragonfly's mission planning, the wind patterns that determine landing safety, the dune field structure that maps potential sampling sites, the atmospheric density profile that constrains rotor design. In this sense, Cassini's contribution to the next mission to Titan is not merely scientific inspiration, but operational necessity. The mission cannot be planned without the data Cassini collected. The machines talk to each other across time. Cassini speaks to Dragonfly through data archived in servers in Maryland and California, in papers published in journals accessible online, in the minds of scientists who spent years working with Cassini's measurements and will spend years advising Dragonfly's science planning. The connection is real, if not direct. This is how science accumulates, not in isolated discoveries, but in chains of missions and measurements and questions, each building on what the last established, each revealing the next question to be asked. Saturn itself, not its moons, not its rings, but the planet, continues to offer unsolved problems. The interior structure revealed by the grand finale gravity measurements is still being modeled. The fuzzy core, the diffuse partially dissolved interior region, extending far beyond what simple models predicted, has implications for how gas giants form and evolve that are still being worked out. The standard model of giant planet formation, called core accretion, predicts that a rocky or icy core accumulates first and then captures a hydrogen-helium envelope from the surrounding nebular gas. The mass and structure of that initial core affects everything about the planet's subsequent evolution: how fast it contracts, how much heat it retains, how its magnetic field develops. If Saturn's core has been dissolving into the surrounding metallic hydrogen for 4.5 billion years, then the planet's interior today bears little resemblance to the planet's interior when it formed. The history is written in the current structure, but reading that history requires models of processes, the mixing of heavy elements into metallic hydrogen under conditions of extreme pressure and temperature that are not yet fully understood. Laboratory experiments that recreate the pressure and temperature conditions of gas giant interiors are being conducted at facilities equipped with diamond anvil cells and laser shock systems. These experiments compress small amounts of material to pressures exceeding millions of times atmospheric pressure, briefly and incompletely mimicking the conditions deep inside Saturn. The results inform the theoretical models. The models are constrained by Cassini's data. The data sits in the archive. The chain runs from a spacecraft that no longer exists to experiments in laboratories on Earth through the medium of mathematics and the practice of science. Saturn's rings, meanwhile, are losing mass. The ring rain that Cassini measured, material falling from the rings into Saturn's upper atmosphere at a rate of several thousand kilograms per second, is one component of a broader ring mass loss process. Micrometeorite impacts on ring particles eject material outward. Plasma interactions charge ring particles and alter their trajectories. Gravitational perturbations from Saturn's moons drive material out of the ring plane. All of these processes remove mass from the ring system over time. At the rates Cassini measured, the rings would be entirely consumed within 100 million years. This number comes with uncertainty. The mass loss rate may have been higher in the past, during periods of more intense micrometeorite bombardment, or lower if some process that Cassini's measurements did not capture recycles material back into the rings. But the direction is clear. The rings are transient. They are getting thinner. They are getting less massive. In the cosmic future, they will be gone. Whatever gave Saturn its rings, the disruption of a moon, the capture of a comet, the remnant of a larger primordial ring system, happened relatively recently and will not last. The rings that make Saturn the most visually recognizable planet in the solar system, the rings that have appeared in every image taken since Galileo first noticed them in 1610 and could not understand what he was seeing, the rings that Cassini spent 13 years studying in more detail than any other instrument had ever achieved. Those rings are temporary. This too is a finding of the Cassini mission, not a discovery of something new, but a measurement that transformed a qualitative understanding. Rings change over time into a quantitative one. Rings change at this rate, with these consequences, on this time scale. The universe does not keep things forever. Rings disperse. Moons are disrupted. Planets cool. Stars burn out. The structures that seem permanent on human timescales are, on cosmic timescales, transient arrangements of matter and energy passing through a particular configuration on their way to some other configuration. Saturn's rings are a transient arrangement. So are Saturn's moons. So is Saturn. So is the Sun. The permanence that human perception attributes to the sky above, the unchanging stars, the eternal planets, is a function of timescale. From a position outside the solar system, watching it in time-lapse across billions of years, everything is in motion, everything is changing, nothing holds its form. Cassini observed one small piece of that change over 13 years with instruments that measured real quantities at real times in a real place. The change it observed was small. Saturn did not noticeably alter its appearance during the mission's duration. The rings did not visibly thin. The moons did not drift to new orbits, but the measurements were precise enough to detect changes that the eye could not see. The mass flux of ring material, the drift of orbital periods, the gradual recession of some moons, and approach of others under tidal forces. The solar system is dynamic on every timescale, and Cassini measured the dynamics at the timescale of a mission. The results are in the archive. The archive is accessible. The science is ongoing. Outside JPL, the months after the mission's end passed as months do. Seasons changed in Pasadena. The team members who had gathered for the final transmission dispersed to other projects, other missions, other institutions. Some retired, some moved to universities, some continued working on Cassini data, mining the archive for signals that had not yet been extracted. The hallways of JPL that had been decorated with Cassini images, the backlit plumes of Enceladus, the hexagonal polar storm, the pale blue arc of Titan against the rings, continued to be decorated with those images. The mission was over. The images were permanent, and the data kept producing papers. In the years following the mission's end, analyses of the grand finale atmospheric entry data resolved questions about the composition of Saturn's equatorial upper atmosphere that had been debated for decades. The ring rain measurements were refined and extended, producing tighter constraints on the ring mass loss rate. The fuzzy core model was developed in more detail, tested against the gravitational field data, and published in journals that circulated among the small community of people who think carefully about the interiors of distant planets. The magnetic field alignment problem remained open, but new theoretical proposals based on Cassini's data were being developed and tested. The mission had ended. The science had not. This distinction between a mission's operational end and the end of the science it enables is one that takes time to appreciate. In the immediate aftermath of a mission's conclusion, attention focuses on the operational fact. The spacecraft is gone, the real-time data stream is closed, the era of new measurements is over. This feels like an ending, and in operational terms it is. But science does not operate in real time. Science operates in the time of analysis, interpretation, publication, and synthesis, a time that unfolds over years and decades after the measurements are made. The measurements Cassini made in September 2017 will still be generating new papers in the 2030s and 2040s as methods of analysis improve, as theoretical frameworks develop, as new questions are asked that make previously uninteresting data suddenly relevant. A dataset gathered over 13 years from a system as complex and poorly understood as the Saturnian system does not yield all its information immediately. It yields it gradually as the community of researchers with the skills and interest to analyze it asks questions that the data is capable of answering. Some of those questions have not yet been formulated. They will be formulated by scientists who are currently students, learning the methods and building the knowledge base that will let them recognize, in Cassini's archive, measurements that answer questions they have not yet learned to ask. This is the temporal depth of scientific data. A measurement made in 2017 answers a question asked in 2034. The connection is real, even though it crosses decades. The data is patient. It waits. Saturn does not wait in any meaningful sense. It simply continues, as planets continue, as the universe continues, on timescales that render human waiting irrelevant. But from the human perspective, Saturn waits. It is there, at the distance light crosses in 83 minutes, turning under its rings, carrying in its atmosphere the atoms of the most successful Saturn mission ever flown. It will be there tomorrow. It will be there in 100 years. It will be there when whatever mission follows Cassini finally arrives. It has been there for 4.5 billion years, and the 83 light minutes between it and Earth are on that timescale a negligible interval. The silence after Cassini is not empty. It is full of Saturn continuing to be what it is in the absence of the instrument that knew it best. The hexagonal polar storm rotates at Saturn's north pole, as it has for longer than any instrument has observed it. 6 sides, each approximately 13,800 kilometers long. The geometry is a consequence of fluid dynamics, a wave pattern that forms in the boundary between air masses, rotating at slightly different speeds, a phenomenon that can be reproduced in a laboratory using a rotating tank of water and a slight differential in rotation rates between the inner and outer sections. The mathematics that produces Saturn's hexagon produces a hexagon in a laboratory tank. The universe is consistent. Inside the hexagon, a deep cyclonic storm rotates. Its eye is 2,000 kilometers wide. For comparison, the entire state of Alaska is less than 2,000 kilometers across, at its widest point. The storm has been continuously observed by Cassini for years, and before Cassini was detected in Voyager data from 1980, which means it has persisted for at least 4 decades of human observation, and likely for much longer. It is rotating now. The hexagon is there now. Enceladus is erupting now. The plumes are rising 200 kilometers above the South Pole, carrying water from an ocean that has been in contact with a hydrothermal seafloor for hundreds of millions of years, releasing that water into space, where some of it falls back onto the moon's surface, and some of it becomes part of Saturn's E-ring, the diffuse outermost of Saturn's named rings, maintained almost entirely by material ejected from Enceladus's geysers. The E-ring is there now. It is thin and diffuse, detectable in the right geometry of sunlight and shadow, a faint halo of water-ice particles surrounding Saturn at the orbital distance of Enceladus, continuously replenished by material from an ocean that Cassini confirmed contains the chemical conditions for life. Titan is there now. Its methane rain is falling somewhere on its surface. The models suggest that methane precipitation occurs during summer in the hemisphere currently experiencing summer, as the sun warms the atmosphere enough to drive convection that lifts methane vapor high enough for it to condense and fall. The rivers are flowing in whatever season it currently is on Titan, flowing with liquid methane towards seas of liquid methane near the poles, evaporating back into a nitrogen atmosphere, cycling as Earth's water cycles but with different molecules, different temperatures, the same physics. The dunes are there, the Huygens landing site is there, the rounded ice pebbles on the plain, photographed for 94 minutes in January 2005, unchanged since the probe's batteries died, unchanged since Cassini's last radar pass, unchanged now, because nothing on Titan changes quickly at human timescales, because the surface processes operate at rates measured in thousands of years per meter. All of this is happening right now. Not observed, not measured, not recorded, but happening because physics does not require observation to proceed, because Saturn has been there for 4.5 billion years without anyone watching, because the universe is not a performance that pauses when the audience leaves. Cassini watched for 13 years, then it became part of what it watched. The watching stopped, the universe continued. In the years since the mission ended, the scientific papers have accumulated. The archive has been accessed. The instruments of successor missions have been designed and redesigned and refined, carrying into their specifications the lessons learned from Cassini's performance. What worked, what could be improved, what new capabilities are needed to answer the questions Cassini raised. The people who flew the mission are older. Some have moved on to other things. The mission is, for most of them, the defining professional experience of their careers, the project against which everything else is measured, the thing they will be associated with for as long as anyone tracks the history of planetary science. For some of them, it ended in a room in Pasadena at 6 minutes to 5 in the morning Pacific Daylight Time, when a line on a screen went flat and Saturn was unreachably far away, and the machine they had spent 20 years working on was dispersing into a hydrogen-helium atmosphere, and there was nothing left to do. For others, it has not ended yet, because they are still working with the data, still finding things in the archive that answer questions they have been carrying for years, still writing the papers that will appear under the heading of Cassini in journals long after the spacecraft itself has become, literally, part of the planet it studied. This is the only honest way to describe what a planetary mission is, not a transit with a destination and a return, but an investment in knowledge that pays returns indefinitely after the initial capital is spent. The spacecraft is the capital, expensive, technically demanding, requiring decades of preparation and execution. But once spent, once the data is collected and transmitted and archived, it generates returns that compound over time. The full archive, every measurement, every image, every telemetry record from 13 years of operation, those are the returns. 753 scientific papers published from Cassini data since the mission ended, and that number grows as the community continues to work. The return on the investment in understanding is incalculable because understanding does not have a price. It has consequences. Some of those consequences are practical. The discovery of Enceladus's ocean has redirected astrobiology programs, mission planning, instrument development, funding priorities. Some of them are less tangible, but no less real. The knowledge that an ocean with hydrothermal vents exists beneath the ice of a moon of Saturn, that the conditions for life as we understand it are not unique to Earth, that the same chemistry operates in the same ways in a different ocean in the outer solar system. This knowledge changes the context in which every subsequent question about life in the universe is asked. That is what a mission leaves behind. Not the hardware. The hardware is gone, dispersed into Saturn's atmosphere, indistinguishable from the planet itself. Not the operations, the mission control procedures, the command sequences, the trajectory calculations. All of these are archived but not active, memories of a practice that no longer has an object to practice on. Not even the spacecraft itself, which exists now only in photographs and scale models, and the detailed engineering drawings and archives that record what it was before it became what it is. What remains is the understanding and the question. And Saturn. Saturn is out there right now, the sixth planet from the Sun, ringed and enormous and ancient, at the distance where sunlight arrives 79 minutes after leaving the star. Its atmosphere is circulating. Its magnetic field is threading through metallic hydrogen deep in its interior and emerging into space in a configuration that theory has not yet explained. Its moons are orbiting, Enceladus erupting, Titan raining methane, the dozens of smaller moons sweeping gaps and waves through the ring material. In its upper atmosphere, at altitudes that no instrument has sampled since September 15th, 2017, the atoms of a spacecraft are dispersed through hydrogen and helium, mixed by winds that circle the planet in weeks, spread across the entire atmospheric envelope of a planet larger than 1,000 Earths. The atoms are not identifiable as spacecraft atoms. They are not labeled. They are not in any arrangement that preserves the structure of the thing they once were. But they are there, and they will remain there for longer than the civilization that sent them. The rings of Saturn are in one sense a solved problem, and in another sense entirely unsolved. The solved part, their composition, Cassini's visual and infrared mapping spectrometer, VIMS, analyzed the spectral signature of ring material across hundreds of targeted observations, building a comprehensive picture of ring composition that confirmed what earlier observations had suggested and added detail that no earlier observation could provide. The rings are approximately 95% water ice by mass, with trace amounts of rocky silicate material, organic compounds, and iron oxides distributed unevenly through the ring system. The ice is not pure. It is contaminated by material accreted from micrometeorite impacts over millions of years, slowly reddening the initially bright white of freshly crystallized water ice toward the subtle pale tan that gives Saturn's rings their characteristic color in natural light images. The compositional variation across the ring system is not random. The B ring, the brightest and most massive of the main rings, is more nearly pure water ice than the A ring or the C ring. The C ring, closest to Saturn of the three main rings, shows higher contamination by silicate material, consistent with a longer exposure to the infall of micrometeorite debris, or a different origin than the outer rings. The F ring, a narrow braided structure at the outer edge of the A ring, is dynamically active in ways that the broader rings are not maintained and shaped by the gravitational influence of two small shepherd moons, Prometheus and Pandora, whose slightly different orbital periods create the braided structure visible in Cassini's closest approaches to that region. The unsolved part, where the rings came from. Three main hypotheses compete for the status of most probable explanation. The first proposes that the rings are remnants of a primordial disk of material that never accreted into a moon, material that was prevented from coalescing by Saturn's tidal forces, which exceed the self-gravity of any body within the Roche limit, approximately 2.5 Saturn radii from the planet's center. Inside the Roche limit, tidal forces tear apart any object that tries to hold itself together by its own gravity. The rings lie entirely within this region. The second hypothesis proposes that a moon, or several moons, once existed inside or near the Roche limit and were disrupted by a collision, their material spreading into the ring system seen today. The candidate disruptor could be a large cometary impactor, or the gravitational interaction of multiple moons in unstable orbits, or the tidal disruption of a single moon that migrated too close to Saturn. The third hypothesis, supported by the grand finale mass measurements that imply a relatively recent origin, proposes that the rings formed when Saturn captured a large comet or Kuiper belt object, and its tidal disruption spread ring material across the equatorial plane. The organic material detected in the rings by Cassini's instruments is consistent with the composition of cometary nuclei, rich in complex organic molecules formed in the cold outer solar system over billions of years. Each hypothesis makes predictions that can be tested, in principle, by future measurements. The mass of the rings, now constrained by Cassini's gravity data to approximately 40% of the mass of Saturn's moon Mimas, rules out some scenarios and constrains others. The age estimate of 10 to 100 million years rules out the primordial disk hypothesis, which would predict a ring age comparable to the solar system's age of 4.5 billion years. But the distinction between a disrupted moon and a captured comet requires measurements that Cassini could not make, and that no future mission has yet been designed to make. The rings remain a partially solved problem. The moons are a partially solved problem of a different kind. Saturn has 83 known moons as of the most recent count, a number that increased substantially during Cassini's mission, as the spacecraft's cameras detected small moonlets, previously too faint for ground-based observation. The largest, Titan, accounts for the vast majority of the total mass of Saturn's moon system. The second largest, Rhea, is less than 1/6 of Titan's diameter. Then Iapetus, with its striking two-tone surface, one hemisphere as dark as coal, the other as bright as fresh snow, which Cassini revealed to be the result of two processes: dark organic material swept up as Iapetus orbits, leading edge forward through the debris field of outer moon Phoebe, and a thermal separation process by which dark material, once present, absorbs more sunlight and migrates to the warmest regions, while the bright icy material remains in permanently shadowed areas. Then Dione, Tethys, Enceladus, Mimas, and dozens of smaller bodies, ranging from irregular captured objects a few kilometers across to geologically complex moons hundreds of kilometers in diameter. Each has its own history. Each carries evidence of the conditions that formed it, modified by billions of years of bombardment, tidal heating, and the gravitational interaction of the entire moon system. Cassini visited most of them, Not all received targeted flybys. The mission's science priorities and trajectory constraints meant that some moons were observed only from a distance, but the imaging and spectral mapping that Cassini performed across the entire system built a picture of the Saturnian moon family that no single mission had ever achieved before. The moon system as a whole is gravitationally complex. The moons interact with each other through mean motion resonances, orbital configurations in which two moons' orbital periods are in simple integer ratios, causing them to gravitationally perturb each other in regular recurring patterns. Enceladus and Dione are in a 2-to-1 resonance. Enceladus completes 2 orbits for every one completed by Dione. This resonance forces Enceladus's orbit to remain slightly elliptical rather than perfectly circular, and that slight eccentricity as Enceladus moves from the closest to the farthest point of its orbit causes the moon to flex under Saturn's changing tidal forces. The flexing generates heat. The heat melts the interior. The liquid water accumulates in the subsurface ocean. The ocean communicates with the surface through fractures at the South Pole. The geysers of Enceladus are ultimately a consequence of orbital mechanics. The gravitational relationship between Enceladus and Dione, the ellipticity of Enceladus's orbit, the tidal heating of its interior. The chain of causation runs from the orbital dynamics of the entire Saturn system down to the individual water molecule rising in a geyser plume from the south polar fractures. Everything is connected. The data Cassini returned makes those connections visible. Cassini measured the tidal dissipation within Saturn itself, the rate at which Saturn's gravity raises tidal bulges on its moons, and the rate at which those bulges are damped by Saturn's internal friction, causing energy to be transferred from the orbital motion of the moons into heat within Saturn's interior. The measurement surprised the mission scientists. Saturn's tidal dissipation rate was much higher than theoretical models had predicted, implying that the moons are migrating outward from Saturn much faster than earlier estimates suggested. If the moons are migrating outward faster than expected, then at some point in the past they were closer to Saturn than they are now. Tracing that migration backward in time suggests that several of Saturn's mid-sized moons, Tethys, Dione, Rhea, may have been much closer to Saturn a few 100 million years ago, potentially interacting in ways that generated heat, altered surface geology, and modified the ring system. The current configuration of the moon system is not the eternal configuration. It is a snapshot of an ongoing evolution. The snapshot Cassini took over 13 years of orbit revealed more change, more ongoing evolution, more active processes than the system had been imagined to contain before the mission began. A small moon with active geysers, a large moon with a methane cycle and complex organic chemistry, a ring system losing mass at a measurable rate, a planet with an unexplained magnetic field and a dissolving core, a moon system migrating outward faster than theory predicted. Active, dynamic, changing. This is what Cassini found in a system that had been considered, before the mission, as relatively quiescent, a gas giant in its moons, interesting but static, geologically dead except perhaps for some residual activity on the larger bodies. The reality was a system in motion, a system generating heat and chemistry and geological activity through processes that were ongoing at the moment of observation and have been ongoing ever since. The universe does not present static objects for inspection. It presents processes, ongoing, connected, changing. The instruments that can measure those processes accurately, precisely, over sufficient time are the instruments that reveal what the universe is actually doing. Cassini was such an instrument for 13 years. There is a way of thinking about what happened on September 15th, 2017, that the mission documents do not record and the scientific papers do not mention. Somewhere in the final seconds of Cassini's transmission, after the thrusters had reached their limits, after the antenna had begun its slow drift away from Earth, after the carrier wave had started to flicker on the screens in Canberra, the spacecraft was tumbling. It was tumbling the way any object tumbles when the forces holding it in a preferred orientation are suddenly removed, not violently, not with any drama that the spacecraft itself could register. Just a slow, aerodynamically driven rotation, the irregular shape of the vehicle finding its own relationship with the thickening gas rushing past it at 31 kilometers per second. In those final seconds, as the antenna swept away from Earth and the signal fell below the threshold of detection, Cassini's cameras were still powered. They were still collecting photons. The data those photons generated was no longer being transmitted. The antenna was pointed elsewhere, into Saturn's sky, into the deep atmosphere below, into the dark of the outer solar system, but the instruments did not know this. They continued what they had been built to do. What Cassini saw in those final seconds, with its cameras sweeping across Saturn's upper atmosphere, was something no human instrument had ever recorded and no human eye would ever process. The view from inside Saturn's thermosphere, looking outward, the faint arc of the planet's limb against the black of space, the distant smear of the rings seen nearly edge on from within their plane, the pale point of the sun diminished to less than 1% of its Earth-sky brightness. And below, or above, depending on the tumble axis, the bands of Saturn's cloud deck, still hundreds of kilometers deeper than Cassini would ever reach, yellows and whites and pale ochres that human eyes had photographed from orbit for 13 years, but never from this angle, never this close, never from inside the atmosphere that contained them. This data was never received. The transmission link was broken. The photons that fell on those sensors in those final seconds generated electronic signals that were stored in Cassini's onboard memory and never downlinked because there was no transmission window left, because the antenna was tumbling away, because the data had nowhere to go. The memory chips that stored those final images were, minutes later, vaporized along with everything else Cassini had been. What Cassini saw in its last seconds is gone. It exists, if it exists anywhere, only as a description of what must have been there, calculated from the known trajectory, the known atmospheric structure, the known camera parameters. The image can be reconstructed mathematically. The image that was actually captured cannot be retrieved. This is the hardest version of the distance that defines all deep space exploration, not the 83 minutes between event and knowledge, which at least delivers the knowledge eventually, but the final seconds of a transmission that ended before the data could cross the void, information that existed briefly in the circuits of a machine and then ceased to exist when the machine did. The universe keeps no copies of what goes unrecorded. What Cassini saw at the end belongs to Saturn now. The silence that settled over JPL on the morning of September 15th, 2017, was not the silence of failure or loss in any final sense. It was the silence that follows completion, the particular quiet of a thing that has been done, thoroughly and without reservation, exactly as it was meant to be done. 20 years of work, 6.7 billion kilometers traveled, 13 years in orbit around a ringed world, 294 engine burns executed without error, one final transmission lasting until physics would allow no more. And then the line went flat, and the screens were quiet, and somewhere 1.5 billion kilometers away in the dark between the planets, Saturn kept turning, as it is turning now. As it will keep turning long after every record of the mission has been forgotten, long after the civilization that built the mission is gone, long after the oceans that covered Earth when Saturn formed have evaporated in the expanding heat of an aging sun. Saturn turns. Enceladus erupts. The rings slowly thin. The universe does not stop. It simply continues in the patient way of things that have no reason to hurry, in the silence between one observation and the next, carrying within it every question that has ever been asked about it and every measurement that has ever been made of it, indifferent and vast and, for those who look carefully enough, astonishing. If you found this story worth staying awake for, even a little longer than you meant to, a subscription means everything to this channel. And if this is where you drift off tonight, that is exactly where this story was meant to take you. Everything you heard tonight is real. Cassini is out there right now, part of Saturn, 1.5 billion kilometers away. Good night.